Hello everybody, my name is Dominic Ferry, joined today with Tyler Creighton, and together we make up Team Iradion, who are focusing on automatic laser optimization. So a quick introduction to Iradion Laser. They're a small company that focuses on the design and manufacture of a large array of high-power CO2 lasers. Their power output ranges from about 30 watts to 250 watts, so we are dealing with very, very high-powered lasers. And their product line is rapidly growing for a number of different applications.
I'll tell you a little bit about the basics of the CO2 laser. We can see there's a glass tube filled with carbon dioxide. This carbon dioxide is introduced to a high voltage, which stimulates the carbon dioxide, which releases light radiation. These photons of light bounce back and forth between these two mirrors, increasing in intensity and power, until eventually being output as a laser beam. If you zoom into those mirrors, you can see the internal mirror mounts for our design. These mirrors have 3 screws which are turned to change the angle of reflection of our mirrors. When you change the angle of reflection of the laser system, you change the characteristics of the laser beam, namely the power output and the beam profile. Now, the power output might be self-explanatory, but the beam profile is the spatial distribution of power within the laser beam. Currently, these characteristics are tuned by hand, and in order to get to the values required, these need to be very precise. Turning currently is inaccurate, which means it's time-consuming, taking upwards of 8 hours for engineers to be able to properly tune these lasers. This, in turn, slows down production. Also, in order to calculate these characteristics, the laser needs to be on, which is incredibly dangerous. So that brings us to our best anticipated outcome. Our project needs to be able to fully automate the mirror optimization. It needs to be able to control the angle of reflection. It must be able to change the angle in both true X and true Y movement. It needs to be able to optimize both the power output and the beam profile of the laser. And it needs to be wrapped in a user-friendly GUI and be portable, safe, robust, and accurate. And it all needs to avoid the output of the laser beam.
All right, so one of the first key accomplishments we'll look at is the mechanical side of the project. We begin by using a light position sensor that tracks the reflected beam location. And using this, we're able to create a feedback loop that allows us to control the position. We were able to create a single mechanical part that is able to couple on to the mirror screws and turn all 3 of them. We implement this using stepper motors. Stepper motors are small motors that are capable of breaking a full revolution into many discrete parts. The current stepper motors that we use operate at about 200 steps per revolution, and this is by far a lot more accurate than by hand. We also have to place the motors to the side of the mirror because the laser output beam outputs right above the mirror. As we'll see, here we can see our 3 stepper motors, 1, 2, and 3. The laser output of the laser beam is going to be right here above the mirror. So we can't put the stepper motors directly behind the couplers, otherwise it's going to eat through them. So we place 1 pulley on the stepper motor shaft, we place another pulley on the mirror coupler, and we use a timing belt in order to connect them. This way, when the stepper motor spins, so does the coupler, and thus it turns the screw. Our entire base has been 3D printed, and we have added notches to all the motor mounts. This way, we can adjust them back and forth. This allows the system to adapt to changes in mirror dimensions, as well as allows the user to use different size belts, as well as different size motors. The next key accomplishment is the software, which the user will use to interact with the system. It allows the user to display the current output of the position detector in microradians. It allows the user to input adjustment values, such as the distance that they want the laser beam to move, as well as allow the user to adjust the resolution by changing the sensor distance. We attempted to make the GUI as simple and as user-friendly as possible.
Hardware implementation of our design. So once the user inputs values from the GUI, it is sent over to the FPGA for processing. The FPGA receives input from both the user GUI and the other sensors that we have in our design. It implements all position and optimization algorithms, and it drives our stepper motors. So to look a little bit more in depth in one of our algorithms, namely the position algorithm, we have our mathematical model of the angle of reflection of our mirrors based on changing the 3 screws. You can see that each of these screws have a distance vector that as you turn the screw, the angle of reflection moves along that value. So to look at our position algorithm, let's say we start here and want to get there. Where do we get from the black diamond to the green diamond? First, we would turn the top right screw clockwise, move along its distance vector, until we're aligned vertically with our destination. Then we would turn the bottom screw clockwise to drop our current angle of reflection down to our destination. Looking at an overview of our system, we can see that first the user enters data through the graphic user interface. This data is sent over to the FPGA, which in turn decides which motors need to turn, which direction they need to turn, and how many turns that they need to turn. This changes the position of our laser, which is picked up by our position detector. Our position detector then sends the data back to our FPGA about current position in the form of a DC voltage. This needs to be transferred to a digital signal for our FPGA to read, so it goes through an analog digital converter first.
So some of our remaining technical challenges include implementing the true X and true Y algorithm, as well as discovering ways to optimize power and beam profile. Right now, all of our hardware are on very discrete parts, so we have the FPGA separated from the motor drivers, and it's just really difficult right now to move it around and stuff. So we want to place everything on a customized PCB, one hardware part. This makes the system a lot more simpler, a lot more robust, and overall easier to manage. We also need to improve the accuracy of the overall system, as well as reduce external sources of error, such as room lighting and things like that, other things that can mess with the sensors, potentially cause error. So at this time, I would like to say thank you to Iradion's engineering manager, as well as our technical director, Robert Mikowski, as well as our ELECOMP Capstone program director, Dr. Sunak. Thank you very much for this very challenging and rewarding opportunity.
Thank you.